Hello and welcome. In this video, we're going to take a look at the notes for kinematics motion in 2 dimensions. Please remember to pause or rewind the video as needed. Let's begin. We start off with a test your understanding review. Circle any quantities that are vector quantities. Please pause the video and attempt this yourself. Okay, let's see which ones you selected. Acceleration, remember vector quantities have magnitude and direction. So acceleration is a vector quantity. Displacement, force are also vector quantities, as is velocity. Everything else on this list is something that has magnitude only and not direction. Therefore, everything else on this list is what's called a scalar quantity. Now, 2 other vector quantities that are not on this list would be momentum and torque. How do we indicate a vector in the typeface of a book? Well, 2 ways really. A vector is indicated with either a bold type print or with an arrow over the variable. Just like this. Vector A, right, has a little arrow right on top of it. Explain what the components of a vector are. Draw the components of vector A on the diagram to the right and state the components A sub x, A sub y. Well, vector components they are the parts of the vector. That point horizontally and vertically. Okay, so if we look at vector A is pointing up and to the left. So in blue, I'm going to point out what the x component is. So the x part, if vector A is pointing up and to the left, then part of it is going left, A in the x direction, and part of it is going in the y direction, which I'll put in gray. That would be A in the y direction, or A sub y. Notice vector components simply complete a right triangle. So right triangle math, right triangle trigonometry, Pythagorean theorem, things of that nature, those are going to be put in play when we talk about vector components. How do you add vectors graphically? Well, 2 methods. And these 2 methods will be, we will go over them in the examples, okay? But they are parallelogram method and what is called tip to tail method. Okay, now how do we add vectors by components? Well, to add vector by components, you add the horizontal and vertical components separately. How do we find the components of a vector? Okay, well, let V be a vector of some magnitude. Remember, the word magnitude means amount, quantity, size, right? How much. So vector v represents the amount or quantity of some vector. And we're going to point it up and to the right. We're going to say this vector v is pointing up that way. It's pointing at some angle theta above the horizontal. Okay, well in blue, I'm going to put a dashed line to indicate this component here. And I'm going to put a gray dashed line to indicate this component here. Now, rather than refer to them, I'm going to go back and forth because not only is this v sub x, but it's also the adjacent component. That is the better way to refer to it. Because if we flip our triangle upside down and twist it, we need to be able to identify the opposite and adjacent components. Okay, so now the gray component, v sub y, that's referred to as the opposite component. Okay, now from here on out, ladies and gentlemen, I'm going to refer to them as adjacent and opposite components. Okay, the adjacent component will always end up being that vector times the cosine of the angle. So adjacent goes with cosine. There's the shortcut, ladies and gentlemen. I promised you a shortcut. There it is. The opposite component will be whatever the vector magnitude is times the sine of the angle. So adjacent goes with the cosine. The opposite component always goes with sine. And notice you simply multiply times whatever the vector magnitude is. So the vector magnitude times the cosine is the adjacent component. The vector magnitude times the sine is the opposite component. And we're going to be using that same pattern all the way throughout. How do you change a vector's components into magnitude and direction? Well, it's going the opposite way. So in other words, this would be if you had the components. So let's say we have the components now. This time I'm just going to use all one color. So we want to find vector v, the magnitude vector v. We have this component. We have this component. Okay, what we're going to end up doing is essentially Pythagorean theorem, because this would be A, this would be B, and this would be C. So just like a squared plus b squared equals c squared, vx squared plus vy squared equals v squared. So how do we get the vector magnitude? It's Pythagorean theorem. V is equal to the square root of vx squared plus vy squared. Okay, now how do we get the direction? The direction would be the angle in which it points. So for that one, we're going to use a little trigonometry. Well, we know that this is the opposite side of theta, and we know this is the adjacent side of theta. So to get the direction, this is magnitude. To get the direction, we're going to use tan of theta equals opposite over adjacent, or vy over v sub x. Now, to get theta, you have to take the arctangent of both sides. So the arctangent of vy over vx, well, that, ladies and gentlemen, is going to give you the direction. There we go. So we use a combination of Pythagorean theorem and an arctangent formula. We will do these examples in class, so you may skip these temporarily. And let's go to page 3, and let's take a look at these test your understandings. Now, for this test your understanding, it might be helpful if you follow along with the video right now, since the context is lost as far as how to add and subtract vectors geometrically. Okay, so in order to show the resultant vector and to add vectors A and B, or to do vector operations, we're going to use, to add and subtract vectors, we're going to use what is called tip-to-tail method. Okay. Now, this is something we're going to go over in class. So if this looks pretty foreign to you, don't worry, just copy it down for now. It will explain itself as we go over it in class. So let's say vector A is pointing off at this direction right here, 3 units over, 1 unit up. Let's say vector B is pointing in this direction, 2 units over, 2 units down. Now, let's say we wanted to go A plus B. Now, A plus B is not mentioned here, but if I wanted to go vector A plus vector B, what I would do is I would take A. Now, B is pointing in this direction right here. It's this vector right here. I would take the tail of B and stick it at the tip of A, just like that. And the resultant vector would be a straight line from where I start to where I finish. So the blue arrow is the resultant vector of adding A and B. Now, it didn't ask us to do this, but I just wanted to show you what A plus B would look like. So what about A minus B? Well, A minus B, guys, is just going to be A plus a negative B. So how do we do that? Well, A is going in this direction here, so let's draw A. Now, B goes in this direction here.
Tatiana Matthews, report to the attendance office. Tatiana Matthews, report to the attendance office.
If B points down and to the left, that means negative B points up and to the right. So negative B is exactly the opposite of B with the same magnitude, right? Just points in the opposite direction. We take negative B and put it at the tip of A, just like that. So A plus a negative B is A minus B, and the resultant vector is a straight line from start to finish. This would be A minus B. Now, how do we do B minus A? Well, B minus A is going to be vector B plus a negative of vector A. So vector B goes down into the right, like this. I mean, down into the left, excuse me, like that. 2 over 2 down. Now, A goes this way. A goes up and to the right, but negative A would go down into the left. It'd have the same magnitude, but it'd be pointing down into the left. So let's take negative A, put negative A at the tip of B. So you've got B, you've got negative A, and this would be B plus a negative A, or B minus A. Draw a line from where it starts to where it finishes, and that would be vector B minus vector A. You can see it's just pointing exactly the opposite direction as A minus B. Now, what if we have what is called a scalar multiple? A scalar multiple is when we do something to a vector to resize it. So if B is, I'm going to show B in black here. B is this vector right here. That means 2b is just going to be a vector that's twice as long. So 2b would be 4 units long, not 2 units long. So we would go 4 units over 4 units down instead of 2 units over 2 units down. Half of b, well, instead of going 2 over 2 down, we're going to go 1 over 1 down, just like that. That would be half of b. And then lastly, negative half of b would be half of b, but in the opposite direction, going this way. That'd be negative half of b. Okay, go ahead and skip the examples for now. And let's move to section 3.2. Newton's second law in component form. Now, I will always abbreviate Newton's second law. Newton's second law will be abbreviated by me as N2L. And we can start off by saying a net force causes a mass to accelerate. Now we're going to take that sentence and break it into an equation. All right, so let's translate this equation into, translate this sentence into an equation. So the first part is this part called net force. Net force is going to be translated into the symbol sigma F. Now, sigma, this is the Greek letter sigma. The Greek alphabet always has upper and lower cases. That's the uppercase sigma. Now, typically in mathematics, sigma usually means sum, adding something. So sum of forces, total force, or you can refer to it as net force. That's the way I'm going to call it. I'm going to call it net force. Causes, that would be equals a mass, m, to accelerate, a. Net force equals ma is our equation for describing Newton's second law, which describes when systems accelerate. When objects or systems of objects accelerate, we will use this. Now, net force itself can be broken down into a causing force minus an opposing force equals ma. So what I can do, ladies and gentlemen, is I can take this phrase here, sigma f, and I can rewrite that in terms of a force that causes acceleration to happen minus a force that opposes the acceleration, okay? And set that equal to ma. Now, instead of writing causing and opposing, because that's pretty long and not too efficient, I'm going to call causing force Fc, opposing force Fo, equals ma. This, ladies and gentlemen, is the formula that we're going to use to describe the forces that cause acceleration. In other words, Newton's second law. Section 3.5, projectile motion. When an object is a projectile, what shape does the path travel? The answer is not arc. Well, the path or trajectory is the path that it takes through the air, is a parabola. Now, let's take a look at this right here. Now, it does say that you could look at conceptual exercise 3.7 in the electronic textbook, but feel free to follow along with the video here. You can do either. How is the direction of velocity related to the parabolic path at each point? So a projectile might look like this. An object flies through the air, right? And we can talk about the velocity as being tangent to the parabolic path. And that's exactly, each of those blue arrows is a velocity. So velocity is tangent to the parabolic path. Sometimes I will use the word path, sometimes I'll use the word trajectory. You need to know it's the same thing. What happens to the horizontal component of velocity? Well, as we're about to find out, the horizontal velocity component, of velocity remains constant. What happens to the vertical component of velocity as it travels? Well, the vertical component decreases to 0 on the way up. So as the object goes up like this, the vertical velocity decreases to 0. Then it increases on the way down. Because again, gravity's pulling on it to slow it down going up and speed it up going down. So it decreases to 0 on the way up and increases from 0 on the way down. At what point in the path is the vertical velocity component equal to 0? At the top. At the top, right here, the object has changed directions and is going from up to down. That is the point at which the vertical velocity component is 0.
Alina Castro, report to the counseling center. Alina Castro to the counseling center.
At what point is the At what point in the path is the speed of the projectile 0? The speed is never 0. Because even at the top, you might have a vertical velocity equal to 0, but you do have a horizontal velocity going across the top. So a projectile is always in motion. The speed is never 0. At what direction, what is the direction of the net force on the parabolic path? The net force, which is gravity, always acts downward the whole way. So if my arrow here is gravity, force due to 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 gravity. You can see the force due to gravity is always acting downward no matter where that object is. What is the acceleration? Well, according to Newton's second law, net force causes an object to accelerate. So whichever way the net force points, that's the way the acceleration points. So if the net force is pointing down, then that means the acceleration is also down. And that would be g. Forgive the messiness of this picture right here, but the acceleration will also be downward. Acceleration always points in the direction of the net force. In this case, the net force is due to gravity, so the acceleration is also always downward. And it's due to gravity. It's little g. Little g is the acceleration for acting on a projectile. Now, let's take a look at the horizontal and vertical motion. So horizontally, the object is moving with constant velocity. We'll explain this more a little bit in class as to why. Vertically, it is free fall, acceleration, due to gravity. The position equation for the horizontal direction is x equals v naught t. Well, technically it's x equals x naught plus v naught t plus 1/2 a t squared. But here's what I'm going to do. I'm going to put a v naught x here, an a in the x direction here, and I'm going to cancel some things. One, the initial position is always 0 unless we're told otherwise. Since we're moving with constant velocity, we have 0 acceleration in the x direction. Therefore, the remaining equation is x equals v naught x times t. We will describe what v naught x is in a minute. The velocity equation is going to be v equals v naught plus at. And again, we're going to put little subscripts here. V in the x direction, v naught in the x direction, a in the x direction, which is still 0. So what that tells us is the velocity in the x direction is the same as the initial velocity in the x direction. Wait a minute, what is this? This is a statement of constant velocity. It's not changing, right? And then lastly, that value of v naught x we talked about, we can get that if this is our v naught, this would be our v naught in the x direction. This would be our v naught in the y direction. Since v naught x is the adjacent side of the triangle, adjacent always goes with cosine, v naught x is going to be v naught cosine of my angle.
Whereas v naught y is going to be v naught times the sine of my angle, because the opposite side of the triangle always goes with sine. So my initial velocity in the x direction, v naught x, will be v naught times the cosine of my angle. Now let's talk about the position and velocity and initial velocity equations for the vertical direction. The vertical equation would be y equals y naught plus v naught yt minus 1/2 gt squared. Notice all we're really doing is just giving a direction to that initial velocity, that's all. V in the y direction is going to be equal to v naught in the y direction minus gt. It's the free fall equation, I'm just giving the velocities a y direction. Lastly, v naught y is equal to v naught times the sine of the angle. Now, this projectile exploratory activity we will do in class. Let's take a look at one final thing, and that is this test your understanding here.
Okay, so instead of pausing to try this test your understanding, follow along with the video so that you can gain some insight into how the velocity vectors change and how the components change for the velocity vectors in a projectile problem. Let's begin. So we've got this object flying through the air with an initial speed of 50 meters per second. And what we have here is a 37-degree angle. And anytime we see that 37-degree angle, we should know that we have 37, 53, 90. This is a 3, 4, 5 triangle. So since this is 50, this would be what? 50, 40, and 30. Okay, and we can kind of figure that out using a little bit of trigonometry as well. So one of the things that we can set up in the beginning of the problem is that the cosine of 37 degrees is about 4 over 5. Okay, according to this right here. Cosine of 37 is 4 over 5, which is 0.80. And the sine of 37 degrees is 3 over 5, which is 0.60. So now, if I want to find V naught x is V naught times the cosine of the angle, which would be 50 times the cosine of 37, or 0.8. And 50 times 0.8 is 40. And then V naught y is going to be V naught times the sine of that same angle, which would be my V naught, my initial velocity of 50, but times 0.6 this time, which is 30. So you can see we get, if we put the vector components on here, I'm going to do I'm going to do the x components of the velocity in blue all the way across. There we go. Okay, and now so for that horizontal component is V naught x, and that's going to be 40 meters per second. Now the gray, now before we move on, if you notice, the velocity vectors in the x direction are constant. Think of it this way. If there's an object flying through the air and there's no wind resistance and there's nothing pushing it from behind, then there's no reason for it to speed up or slow down. Therefore, it will move at a constant speed in the x direction. So the initial speed in the x direction is the same horizontal velocity in the x direction all the way through. So I'm going to copy this all the way across. Now at the top, all you have is x direction velocity. There we are. And then in the y direction, I'm going to put that in gray. So in the y direction, we start off with, oops. There we are. We start off with v naught y, which was 30. And if you look, ladies and gentlemen, it's that same 3, 4, 5 triangle, or 30, 40, 50 triangle. Same ratio. Now notice the gray component, v naught y, or I should say vy in this case, is getting smaller and smaller until it is 0 at the top. Because gravity is obviously pulling in the negative direction. Now, the actual value of Vy is going to be completely dependent on the time at which it gets to these points. Right here and right here. Meaning Vy is equal to V naught y, which was 30, minus g times t. So to summarize, velocity in the x direction remains constant. So it's constant velocity going horizontally, okay, all the way. Because we are assuming no air resistance, and we're assuming nothing is pushing it from behind. Therefore, the net force acting on it horizontally is 0. Therefore, there's no acceleration horizontally. However, Vy does change due to gravity. The same way an object does when it's in free fall. So for instance, when an object gets thrown upwards and then it falls back down again, what does it do? It slows going up, right? And then it speeds going down, right? One more point of emphasis. Since the air resistance is considered negligible at the AP1 level, the time it takes to go up is symmetrical with the time it takes to go down. So if the whole trajectory was 4 seconds, then this time to get to the top would be 2 seconds. And this would be the remaining 2 seconds. Okay, we will conclude the examples here on page 7, page 8, page 9 in class. I hope you found this helpful. Please, again, pause or rewind the video as you need to. Thank you.